we spent some time talking about some series and things like the geometric series and how to get the exact value of the sum of the geometric series. But today I want to talk a little bit about something different. I want to talk about the idea of an integral test. Integral test is really powerful. So before we get over here, I want to take a look at this diagram. So if you think about a sequence, and the sequence is some decreasing values. So I have A1, A2, A3, and A4. Those are the outputs of that sequence. We can think of those as heights, so basically the value of the sequence at that index, the value of the sequence at that index, the value of the sequence at that index. So we have the values at each index. But what's neat about this is that all of these are separated exactly by 1. They're offset by 1. What that means is that instead of representing it as a one-dimensional, just a height, we could think of it as a height times a width of 1. So it would have the same value, right? The height and the area of this would have the same magnitude. But they wouldn't have the same dimension, but they'd have the same magnitude. And that's what we're looking for here. So instead of thinking of this in terms of just a value of a sequence, I can think of these as a series of rectangles. And why is that helpful? Well, that's helpful because that's kind of what the definition of an integral is that you have a bunch of rectangles. So now what I want to do is I want to construct a decreasing sequence. I want to say, okay, well, the decreasing sequence, a decreasing function. So if I have some sort of function f that goes through each of those points, but the function is both continuous and guaranteed to be decreasing. So you could construct this however you like. It's always possible to construct a function that does that. If the sequence is decreasing, you could even construct something that's just a bunch of line segments if you had to. But anyway, the whole point on this is that if you do this, then you now have something that's integrable, right? If it's continuous and positive, well, in this case we're going to say positive, continuous, positive, and decreasing, then it's going to be integrable for all finite values. So if we take that integral and we go all the way out to infinity, what we're going to get is an area under this red curve. And that's really neat because if we do the area under the red curve, it's going to closely approximate the value of the area of these. Now, in fact, it actually underestimates it. So the integral, it's always going to be less than these rectangles. But this is using a left-hand approximation. If I did what's called a right-hand approximation, so I take it and I go the other way, so the lines are going backwards, then it's actually going to always overestimate it. And then you have to worry a little bit about this, but it's not as big of a deal as it sounds. And we're not going to get into the rigor of that. But the idea behind the integral test is that depending on how you draw your rectangles, it's either going to overestimate or underestimate the sequence values. So if you do that, you know that the integral has to be, it's between a lower estimation and an upper estimation. So if those bounds are right there in between it, it's sort of like an inverse squeeze theorem. It essentially says that the integral can tie directly to the sequence for the convergence. Why is this useful? Well, this is useful because dealing with sequences and series is kind of gross. If I have a sequence and it's a bunch of numbers, I don't know if it converges or diverges. That can be difficult. But if I know that the sequence is a decreasing sequence, it would decrease all the time, and I can write a function that goes through those points to have it decrease all the time, I can just take an integral. When we know how to take integrals, integrals are relatively easy to compute. An example would be this. I have 2n over n squared plus 1. And I'm going from n equals 1 to infinity. And you say, okay, well, how do I do this? Well, if this had been like n squared minus 1, and it would have gone from like 2 to infinity, we could do a partial fraction decomposition. And with the partial fraction decomposition, we might have been able to do a telescoping series. We might have been able to figure something out, maybe. But if I instead say, okay, well, what if I take a function that is that sequence, 2x over x squared plus 1. If I were to plot this function, it would be decreasing for all values of x. It's always, it converges to 0. So it passes the nth term test for divergence. But if I integrate it, I get the natural log of x squared plus 1 from 1 to infinity. And if I plug in the bounds here, I'm going to get an infinity minus natural log of 2, which doesn't matter. So I get an infinity, which tells me that directly this diverges. Why is this powerful? Because instead of having to do any of this, I looked at this and said, oh, well, that's positive and decreasing. So I can define a function that is both positive and decreasing. I can take an integral and see the divergence. So like that, it makes your life so much easier. And really, so the nth term test for divergence should be the first thing you always do. You should always try that, because if that fails, then it diverges immediately, which is nice. Now, if it doesn't, the next thing you should do is look at this. If it's positive and decreasing, try the integral test. And we're going to deal with some more tests as time goes on, and we're going to deal with some more interesting series, but we're kind of developing a toolkit of how we should be analyzing these series for convergence.